Okay, so yesterday in class we learned about Bronsted and Lowry, and today in class we did a lab. So I picked a few reactions that we could visually see just to show how Bronsted and Lowry works and how we can predict. So the first example we took a look at was sodium hydrogen carbonate reacting with sodium hydrogen sulfate. So just like before, if you're predicting a reaction, you want to write down everything that is present. So you have the sodium ion, the hydrogen carbonate ion, and you would also have water present, sorry, not H2O, and then from the sodium hydrogen sulfate, you would have HSO3 negative. Then you would go through your data booklet and list all your acids and all your bases, and then you would want to pick your strongest. So if I'm just taking a quick look here, I do see that I have my hydrogen carbonate ion, and up higher over here I have my hydrogen sulfate ion. So this one is my strongest acid, and here is my strongest base, even though I have some more present. So when I pick my strongest, I take my strongest acid, HSO3, and I react it with my strongest base. When I do this, the hydrogen from the acid will go and be donated to the base. So then you are getting SO3 negative 2 and H2CO3. Sorry, with no charge. Now that is our products, and because your acid is higher than your base, but they're both weak, this would be in equilibrium, so the arrow would go both ways, and your products would be favored because of the acid being higher than your base. Now, when it goes to the predictions, you get this extra bit of information that carbonic acid can decompose into water and carbon dioxide gas. So what that's saying is this product here, H2CO3, will decompose into H2O and CO2. Because of that, then it's asking, will we see bubbles? So because we have carbon dioxide as a gas, yes, we should, because that shows us bubbles and the products are being formed. So that should be the prediction. And then we go and do this in the lab. So we have the sodium hydrogen sulfate, the sodium hydrogen carbonate, and when it's mixed together, you can see that it made bubbles, and that would be the carbon dioxide from the product being decomposed. So now here's another one where we're adding sodium benzoate with sodium hydrogen sulfate. So we want to take a look at what's being formed. So if we have sodium benzoate, that would be Na positive, and benzoate is the C6H5COO ion. And it's mixed with sodium hydrogen sulfate, so Na positive and HSO4 negative, and water would be present. So we're going to do the same thing we did before. We're going to pick your strongest acid and your strongest base. So looking at my chart here, it looks like the hydrogen sulfate ion once again is my strongest acid, and the benzoate ion is my strongest base. So I can show that reacting. So HSO4 negative being the acid, reacting with C6H5COO negative being the base. They're both weak, so our arrow would go in both directions. The acid will give away its hydrogen to the base, making SO4 and negative 2, plus benzoic acid, so C6H5COOH. Now your acid is higher than your base, so once again your products should be favored, and then we can come to the prediction. So once we get some more information, it's telling you that benzoic acid is highly insoluble, and would you form a precipitate here? So because all of this is happening in solution, the fact that we are making benzoic acid and it's in solution, yes, products are favored, we're making that acid, we should see a precipitate. And then here is what happened in the lab. We have the sodium benzoate mixing with the sodium hydrogen sulfate, and it's both of these are two clear liquids, and when they go together they make this white solid right away. So that is showing that our prediction was right. Now the last one I put in here has to do with indicators. So here we are told about methyl orange. And if you take a look, and I know this is really hard to see because I, for some reason, made it super small. Methyl orange is right here on page 10 of your data booklet. And each of our indicators, if you look at this first column in, has an acid-base pair. And then it also has Ka values and colors. So Ka can be superimposed on our page 8, 9 of the data booklet. So if we had this methyl orange indicator, we would know where to find it on our acid base page. So when we're looking at it and it says that methyl orange in its base form, again, I know I'm very sorry, this is so hard to say, would be MO negative. It's going to be reacted with hydrochloric acid. Hydrochloric acid is a strong acid, so it will dissociate. And if you're adding in hydrogen ions, you say that you're adding in hydronium. So doing that, the acid will donate a hydrogen to the base. So we'll end up with HMO, which is the acid part of the indicator, plus water. Now, I'm putting my arrow in one direction because I added in that strong acid, so this would not be in equilibrium. Then when it asks about the colors, the base part of your ion is yellow. So this side would be yellow, and then the acid side over here would be red, I believe. Yes, it's red. It's hard to see. Now, if we weren't sure that we had a strong acid and know that the products for sure is going to not only be favored, but we're getting all products, and instead we had to compare it, we would be able to look at the value of the Ka, just seeing it a little bit more clearly here, and we would be able to put it on the table. So this one, if it was 3.5 times 10 to the negative 4, my eyes aren't that great here, 3.5, it would be around here that we would place it. And if you put in those ions, so like the HMO and the MO negative, you could still now figure out, is your acid higher than your base, or is your base higher than your acid, if we weren't dealing with something strong and we had to figure that out. Now, because we are dealing with something strong and we're making all products, then if we had this system, our indicator should make the system red. If reactants somehow were favored, so not in this situation, but reactants were favored, then we would say the system would be yellow. So then we went into the lab and tried it. So we have hydrochloric acid mixed with methyl orange. At the top here, you can see methyl orange is a very orange color, but when you add it, you get this red color. So as always, I hope you found this helpful. If you did, please subscribe and let me know if there's any other video I could ever do for you. Thanks for watching.